Okay, geometry students, today we are reviewing for tomorrow's Unit 7 test, which of course encompasses a ton of information about circles. If you have yet to begin making yourself flashcards for your vocabulary, studying your formulas, running yourself back through old problems, I can't imagine what you're waiting for, but if you're waiting until now, you really need to get busy and get that taken care of because there's a lot of vocab and a lot of formulas. So let's take a quick look back at the information that we have covered here in the last couple of weeks. Okay, now obviously we started off talking about circles being a particular type of shape, very special type of shape. In fact, they were the first non-polygon that we studied this year. And of course, it's not a polygon because a polygon is an enclosed shape that is built entirely out of line segments. Clearly, circles are not built out of line segments, so we came up with a definition for what a circle actually was. And the textbook definition of a circle is that it is a set of all points that are equidistant from a given point. The given point would be the center of the circle, and obviously if you measured outward from the center of the circle in an infinite number of directions and placed an infinite number of points at the end of that measurement, then you end up with a nice, smooth, curved, two-dimensional surface, which we would call a circle. And of course, circles are typically named after whatever their center point is. So circle A, circle B, circle C, and so on. Okay. Now we talked about at the very beginning a relationship between a central angle, which is an angle that has its vertex positioned on the center of the circle itself. Okay. So in this case, we're looking at a central angle that would be angle ABC. Okay, and there's a relationship between that angle and its arc, which we'll get to here in a moment. Okay, but we also came up with a structure that we probably already knew, which was an arc. An arc is a portion of the circumference of a circle, and arcs are named by their endpoints from where those radii make contact with the circle itself. Okay, so in the circle up there, we had arc AC. Okay. Now the relationship between the central angle and its arc is that a central angle and its arc are always going to measure the same when we are talking in degrees. Okay, so whatever the degree measurement of the angle, the central angle is, the degree measurement of the arc will match that, and vice versa. If you know the degree angle or the degree measurement of the arc, then the degreed angle measurement will be the same. Okay. We also broke things down, the sizes of our arcs, into basically three categories. Okay, arcs can be classified as minor arcs if they cover less than half of the circle. They can be classified as major arcs if they cover more than half of the circle. And of course, if an arc were to measure exactly half of a circle, the term for that is semicircle. Okay, now naming our arcs. Okay, in order to name them, okay, we said that arcs would be lazy, that they will if you go two endpoints on an arc, if you do not force the arc to go the long way around the circle, then it will not go the long way around the circle. So in this diagram above, if you say arc AC, that arc is going to begin at A. It's going to travel downwards from A to get to point C because it's lazy. It's going to take the shortcut. So if you are trying to discuss a major arc, then you must list another point going the long way around the circle. In this case, we have a point D that is out there. So if we say arc ADC, then there's no way that the circle can try to cut the short corner there to get from point A to point C. It's got to go the long way around to pick up point D as well. Okay. We also said that we can take arcs and we can add them together or subtract them from each other if we need to in order to make larger arcs or smaller arcs. Okay, and also, if we have arcs that measure the same, then we would say that those arcs are congruent. Okay, so we looked at some examples on some of this vocabulary, and then we moved on. Okay, the next day we took a look at inscribed angles. Okay, difference in inscribed angles is the positioning of the vertex. Okay, if you have an angle that has its vertex on the circle itself and then its endpoints make contact with the circle, that is what we call an inscribed angle. Okay, there's a relationship with the inscribed angles. Okay, and there's two different ways of thinking about it. You can think about it saying that the angle is always going to be half as big as the arc, or the other way of thinking about it is to say that the arc is going to be twice as big as the angle. Mathematically, they both mean the same thing. Some people just prefer one set of vocabulary over the other. Okay, special cases of inscribed angles, and we talked about these theorems and said, you know what, these theorems are not real deep thinking. These are fairly common sense type theorems, at least in a couple of cases. Okay, we said if we have two inscribed angles that have endpoints on the circle at exactly the same location, then the theorem would say that those angles must be congruent. And that makes perfect sense because they both have the same arc measurement. If they both have the same arc measurement and both of the angles will measure half as big as the arc, well, they're both half as big as the arc. They don't have any choice but to be congruent. Also, down at the bottom, okay, we said if you have an inscribed angle that happens to have its endpoints on a diameter of the circle, then that is going to force the angle to be a right angle. Well, again, that's kind of obvious because if that is a diameter in the circle, then that means the arc outside of that diameter is a semicircle. It must measure 180 degrees, and the inscribed angle with its endpoints on that diameter would be half of that 180 degrees, got to be 90. So again, kind of common sense. Okay. This one, not quite so much common sense, but if you get to thinking about it, it also is. I'm not going to go through and explain it again. If you want the explanation of this one, you can go back to the this days of notes and listen to that video. But so I'll just read it basically as it is. If you take a quadrilateral and inscribe it inside of a circle, and inscribe it means that it fits exactly inside of the circle with all four of its vertices on the circle itself, okay, then that means that the opposite angles inside of that quadrilateral are going to be supplementary. Okay. The rest of this was looking at some examples, and then the next day we brought kind of the rest of the truckload of vocabulary into the discussion. Okay, so we already had a definition for circles, but here comes some other stuff. Okay, a chord. A chord is a line segment that has its endpoints on the circle. It does not have to do anything other than have its endpoints on the circle. It does not have to hit the center point. It can if it wants to, but if it's a line segment, it has its endpoints on the circle, then that is a chord. Diameter, okay, is a more specific term for a chord that just so happens to pass through the center point of the circle. A diameter is still a chord, but most specifically, we would call it a diameter, not a chord. And of course, radius is only halfway through the circle, from the circle itself to the center point. That's what we call a radius. Of course, the connection between a radius and a diameter is a radius will be half as big as the diameter, or the diameter will be twice as big as the radius. Whichever way you choose to remember that is fine by me. They both mean the same thing mathematically. Okay, so whichever way you can remember it, it's great. Okay. All right, we had some other types of lines interacting with our circle, this time from the outside in. If we had a line ray or line segment that passed by our circle and only made contact with the circle one time, did not actually enter the interior space of the circle, just kind of glanced it, or glanced off of it on the way by, then that is what we call a tangent. This one location that the tangent makes contact with the circle is what we call a point of tangency. Okay. Now we had a property of tangents. Okay, tangents were always going to be perpendicular to a radius of the circle. Okay, if a radius connected to the point of tangency, then that was going to be perpendicular with the radius. Okay, tangent and radius are perpendicular. Now, if a tangent happened to be tangent to two circles at the same time, okay, it's what we call a common tangent, and those are broken into two subcategories. You can have what's called a common external tangent and a common internal tangent. Common external simply means it does not get into the space in between the two circles. Internal would be it passes through the space in between the two circles. So in the diagram down there, the green one is a common external tangent, and the red one's a common internal tangent. Again, they're both common because they both are tangent to two different circles. This is not real normal type vocabulary. We don't run into this idea of common tangents too often, okay? But while we were talking about them, it made sense for us to go ahead and have a look at those. Okay, a different type of line, ray or line segment that intersects with a circle is what we call a secant. Okay, this time our ray or line segment is actually going to enter into the space of the circle. In so doing, it makes contact with the circle twice. Okay, so a ray or line segment that makes contact with a circle twice is what we call a secant. Now, a little property of a secant is, of course, you can look inside there, inside that circle, and you can see that a secant does contain a chord. Okay, so a little bit of information there. And the rest of that was vocabulary. Okay, after that, we started to take a closer look at some of the properties of these different structures. All that vocabulary we've been doing, okay, we saw that it had a whole lot of properties going on around those structures, okay? So we'd already discussed the fact that a tangent was going to be perpendicular to a radius, and that gives rise to the possibility of right triangles. Of course, anywhere you have right angles, you've got right triangles. That brings Pythagorean theorem or possibly SOHCAHTOA into the problem. Now, we haven't seen a whole lot of SOHCAHTOA, but I mention it every time I mention a right angle or a right triangle because it's always an option. Okay, anywhere that there's right triangles, any of the rules that you have for right triangles may show up. Okay, so we looked at some problems that had this tangent and radius being perpendicular. We looked at that property and started dealing with some of the right triangles. So mostly this was about applying that property to those right triangles and solving from there. So if you have issues with this particular unit or the problems that we worked, that's probably something we're going to have to spend a little bit of time at in tutorials discussing, because that's a skill that you need to get worked out. The only other property that we looked at was very much common sense, and that is what happens if you have a tangent or two tangents, pardon me, that originate from a common endpoint. And common sense, okay, you would probably have a pretty good guess at this one, that if you have two tangents that come from a common endpoint, then their lengths are congruent to each other. Okay, so that was the end of that lesson real quick. Okay, properties of chords and arcs. A little bit more to this one, but these are some properties we're going to have to get memorized. Okay, and the first one dealt with the possibility that a diameter and a chord might be perpendicular to each other inside of the circle. Okay. Now, there's two ways of looking at this, the straightforward property and then the converse. Okay, the straightforward property says if you have a diameter and a chord in your circle, and you know for a fact that they are perpendicular to each other, then what you know about that diagram is that your chord is bisected, as is the arc outside of those chords. Okay. Converse way of looking at it is if you know for a fact that you have two chords intersecting, and you know that they are perpendicular, and you know that the chord or the arcs outside of them are bisected, then that means that that chord that was doing the bisecting is not just a chord, it is a diameter. It's passing through the center point of the circle. So same rule, two different ways of looking at it, and both are valid. So you're just as likely to see the regular rule up top show up as you are the converse down at the bottom show up. Okay, another little rule that comes into play here is if you have two chords that are congruent to each other, okay, or actually two ways of looking at it. If you know for a fact that they are the same distance away from the center point, then that is going to force them to be congruent to each other. The converse of that is also true. If you know for a fact that the two chords are congruent, then that's going to mean that they are the same distance away from the center point of the circle. So we looked at some examples, and I believe that was all. Okay, lines and circles with common endpoints. We spent a good deal of time looking at these situations because there's a lot of different combinations of lines that may begin from a common endpoint. Okay, but as far as the angles that are caught between those two lines and the arcs that are caught between those two lines, there is a rule that applies to all of them. So hopefully we've got this one memorized, that the measure of the angle between those two lines is going to equal 1/2 of the difference between the two arcs that are caught between those two lines. Okay, and we always do the larger of the two arc measurements minus the smaller of the two arc measurements because we do not want to end up with any negative angle measurements. Okay, typically we do not allow things like that to happen in geometry. Later on, if you end up with some trigonometry classes, you may find out that there is very much such thing as a negative angle measurement. We're just not doing that in geometry. Okay, so the rest of this was examples over and over and over again, showing that situation. The measure of the angle is half of the difference between the two arcs. Now, if it's two tangents like you have up at the top example there, those two arcs are going to build the entire circle. Okay, so that one's pretty straightforward. A little bit more complicated if you have a tangent and a secant, because the circle is divided into 3 arcs, so we got to make sure we get the right 2 plugged in, and complicated slightly more when it's 2 secants coming from a common endpoint, because the circle is divided into 4 arcs. We got to make sure we get the right 2 plugged into the formula, and in all cases, the arcs that go into those formulas are the 2 that are caught between the 2 line segments. Okay, so the rest of this should have been examples of how that worked, and then we moved on. Okay, the next thing we did is we looked at some more advanced, or not necessarily more advanced, just some additional formulas that go along with angles and arcs inside of circles. Okay, so we had already looked at that situation where the 2 line segments came from a common endpoint. Okay, but we needed to also now look at the situation where, you know what, that common endpoint might not be outside of the circle like the 3 from the day before we looked at, but that endpoint might actually be on the circle itself, like in the instance of a tangent and a chord intersecting each other, like is shown at the bottom of the screen right now. Okay, this is treated very much the same as yesterday's material, or it's also treated the same as an inscribed angle. So as I told you before, either way you want to think about it is fine with me. You should be able to get to the right answer either way. Okay, but the way it ends up being is the measure of the angle in between the chord and the tangent is going to equal 1/2 of the measurement of the arc also caught between the chord and the tangent. Okay, and again, it would work the same if you use the formula up at the top of the screen. The only difference is there's only 1 arc caught between the chord and the tangent instead of 2. So in the formula up top, you would not have 2 angles or 2 arcs to subtract from each other. You would just have 1 arc in there minus nothing, so it's just 1 arc. Okay, and in either way, it would work out. Okay, now if 2 line segments, in this case chords, okay, if the common endpoint is inside of the circle, okay, inside of the circle we have a very familiar looking formula. The measure of the angle equals 1/2 of something to do with the 2 arcs that are involved. Okay, but this formula, as we have seen before, okay, we've seen a formula that has a minus. The 2 arcs are subtracted from each other. Okay, but in the instance of the intersection being inside the circle, that is actually going to change the sign that's going on in between those 2 arcs. So in this formula that you see now, okay, we should be noticing that it is the sum of the 2 arcs, not the difference of the 2 arcs. That's a very important thing to remember, very important difference between the other formula. And of course, with the way that chords and arcs are positioned inside of a circle, there's actually 2 different positions you can apply this rule into the circle, depending on which direction you're actually wanting to look. Where are the vertical angles at that intersection that you're looking at? Okay, and they might be going side to side, like the one up top, in which case the arcs are also side to side. Okay, could be up and down like the one at the bottom, in which case the arcs are also up and down. Could be diagonally, could be anywhere. Okay, just make sure that you are getting the vertical positioning at that intersection. Okay, examples and more examples, and that was that. Next to last lesson was length of lines in circles. Okay, and this was kind of different. We'd already seen this example, 2 tangents coming from a common endpoint. The rule is the tangents are going to be equal to each other, so that one was not new. However, something that was new is if we had a tangent and a secant coming from a common endpoint, there's kind of a strange relationship between the lengths that are going on here. The relationship basically establishes if you take the length of the tangent and square it, then that should equal the length of the secant to the first intersection with the circle times the length of that secant to the second intersection of that circle. And as we saw, we got to be very careful when we're positioning our values where the secant is concerned, because again, the first one is to the first intersection with the circle, and the second one is from the common endpoint all the way to the second intersection of the circle. So that length outside the circle on the secant seemingly gets counted twice, and it does. Okay, so make sure you get your values in there correctly. If you understand the relationship with the secant going on with the tangent and the secant, then you should understand the relationship going on with two secants, because it's exactly the same thing. When it comes down to lengths, we're going to go on one secant and say, okay, secant, what is your length to your first intersection with the circle, and what is your length to the second intersection with the circle, and we're going to multiply them. And that should equal, on the other secant, what is your length to your first intersection with the circle, and what is your length to the second intersection of the circle, and we're going to multiply those as well. And again, pay close attention to getting your secant information plugged in correctly, especially on that one where it's to the second intersection. The other rule we looked at on this one was when two chords intersect in the circle. Okay, this one is a little bit of common sense, but maybe not so much. Okay, the rule basically says if you take the two pieces of one chord and multiply them, that should equal the two pieces of the other chord multiplied together. The rest of this should be examples. And then we moved on. Okay, area, circumference, sectors, and segments of circles. Okay, this is probably where we need to spend the bulk of our time skill-wise getting prepared for the test, because the hardest math of the unit is in this section. Okay, so aside from vocabulary, pardon me, and formulas and all that kind of stuff, this probably needs to be where we spend more time getting ready than anything else. Okay, now area of a circle, okay, very easy. We know area of the circle. The area of a circle is found by pi r squared. I am not going to give you that formula tomorrow on the test. You've been working this formula since 6th and 7th grade. It's probably time you have it memorized. So if you do not have it memorized yet, I don't know what you're waiting for, but let's get this one done. The area of a circle is found by pi times r squared. And again, I do expect you to just leave your answers in terms of pi, unless the answer choices that you're provided happen to be decimal points. In that case, you will use your calculator, find out what the decimal point is, and then select your answer. Okay. Now, we switched gears a little bit and said, okay, what happens if we're not looking for the entire area of the entire circle? What happens if we're only looking for a fraction of the circle, which is what we call a sector? Okay, well, it's really a very simple conversion here. If you're only looking for a fraction of the circle, then you simply tell your formula what fraction of the area you're actually looking for. And we get that by theta. The two radii that bound the sector, that tell us how big it is. There is an angle measurement in between there at that central angle. Okay, whatever that measurement is, we're going to put it in the numerator of a fraction over 360. It is over 360 because there's 360 degrees in the entire circle. And then whatever the result of that is, we will multiply it by pi r squared. Okay, circumference, again, not new information, something we've done plenty of times before, 6th and 7th grade. Okay, the circumference of a circle is found by multiplying 2 times pi times the radius. Some of you learned it as pi d, pi times the diameter, and that's fine. If you like that formula, use that one instead. Okay, and again, I'm not going to provide you with the formula because it's been a number of years that you've been working with this formula. If you haven't memorized it yet, I don't know what you're waiting for. Get her done. Now, just like with the sector, if we're only looking for a portion of the circumference, which is what we call an arc, we should already know that. Okay, then again, we just need to tell the formula what portion of the circle circumference are we actually looking at, and we tell it that fraction the same way we did with the sector. Theta out of 360 degrees. How much of the circle is actually covered? Take that value and multiply it times 2 pi r. Okay, now a segment. Okay, segment is probably easily the most complicated thing that we've got going on this unit, so it's probably where we need to make sure that we know what we're doing. Segment of a circle is what you get if you connect the endpoints of two radii with a chord, and then look at the area between the chord and the arc. Okay, so if you think of a sector as a slice of pizza, then a segment is basically the crust. Okay, if you eat all the pizza out of there and don't eat the crust, you're basically looking at a segment of the pizza or something very similar. And basically what we said that we are going to do is we're going to treat the segment as what we call a composite shape, meaning we don't particularly have a good description or a good formula to go along with it, or that the formula or description is simply a collection of other shapes that we already know about. And that's where we're looking at for the formula of a sector. There is, or a segment, pardon me, there is a sector. We know sectors, we know how to work with sectors. There is a triangle that is missing from the sector. Well, triangle is a shape that we know and we have formulas for that. So we don't really need a new formula in order to tell us what's going on with a segment, because it's basically a collection of two other formulas that we already know. Sector, theta out of 360 times pi r squared. Triangle, 1/2 times base times height. And again, if you have not memorized the formula for triangle, get over it. Get it memorized. You've been working with it for too many years now to not know it yet. Okay, so we're going to find these two results of these two formulas, and we're going to subtract them, because clearly we do not have the entire sector. It is missing a triangle, and when something is missing in mathematics, well, that is a subtraction issue. We will subtract those two values. Okay, so you find your two values, you subtract them, and again, you can leave the answer just like this, unless it's an answer choice that is multiple choice, in which case you're probably going to have to dump this in the calculator, find out what the decimal point is, and then answer your question. Okay, that is basically the information that is going towards tomorrow's test. Now, obviously, that's a lot of info, a lot of formulas, a lot of vocabulary, a lot of definitions, and so on. Okay, but it's been coming, for 2 weeks now. I've been telling you not to let this pile up on you, so hopefully you have not. Anyway, that's your information. I'll post the video to Edmodo. If you want to listen to it again later on as a way of reviewing, that would be great. We'll see you at the test.